Hello, everyone who is watching us today. I'm very happy to talk about this research today, which started as a very, how can I say, it started like a simple thing, very simple thing in a discussion during a class. But that simple thing that starting during a discussion, during a class, it become really big. And now uh, this is the third time that I'm presenting this research in a different language. It started in Portuguese. I've just presented in Spanish and now in English. So it reached, I would say, like a global audience. I think that it started with a simple conversation, and then I'm very glad to start and share this experience with you. So today I'm gonna present a method called FEV Smart. It's basically a low-cost solution for quality assessment. And our intention was to make a transition from a manual inspection to an automated inspection, and for a specific kind of steel bar, which is reinforcement cage of precast concrete elements. So this is a research, not a standalone effort. It's an effort of three people. The first person, which is very related to this research, is Brenda Araújo. She's now a master's student at the Federal University of Bahia. Alison Silva, who is a PhD candidate and also at the Federal University of Bahia, and myself, who I'm a assistant professor at the Federal University of Bahia, and nowadays I'm a postdoc scholar here at the UC. You can find all these details about this research on this paper published in the journal Park, Research in Architecture and Construction. It's published in English. So if you would like to get a touch or see all the details, because we have today is an overview, but you can find all the details on the paper published last year. Okay. So what will you cover today? Today, you're gonna learn a little bit more about the FEV SMART method. So I divided this presentation in 6 areas. The first one, we're gonna start showing you the problem. So what was the problem that motivated us? And the second area is the context. So we're going to talk a little bit about understanding the precast concrete construction context. And once we know the problem and the context, the third part will be the solution that we developed, call it FEV Smart, as an effective solution for this problem in this context. And then we're going to move on to a technical implementation and bring you some details and aspects of the technologies integrated in the FEV Smart. And then later on, we're going to show to you some results and performances metrics. And at the end, we're going to share with you some key takeaways in future direction, because this research is not done. You know, it started as an undergraduate study, uh, particularly with Brenda, and nowadays she's a master's student and she's still pursuing further develop the FEV Smart. Okay, so let's start with the beginning. Why do we need better inspection? So basically, in a manual inspection, we have pros and cons. So, what is the advantage? What are the advantage of a manual inspection? So basically, we can say that it's very related to the inspector expertise. So his or her experience brings a lot of advantage in a manual inspection. Also, you use basic tools. We need a tape. We sometimes use a paper-based design of the project, and then it's very basic. But on the other hand, is a task which is prone to very subjective errors because it depends of the inspector experience. So if you have a well-experienced inspector, okay, you have a great inspection. But on the other hand, if you have a novice inspector, it can bring some errors to the process. And another advantage, I would say, that is the time consuming because it takes time. We were in a precast company and it that develops a lot of product, and it takes a lot of time to manual inspect each one of the elements, like beams or columns. And in some cases, depending of the scale and the size of these elements, it can also be a very risky task when you're trying to measure and or to check all the elements that we need to check. It can be also a very risky activity. And finally, we have also the unreliable data. In fact, we can bring a lot of errors, and also the type of data that we develop from this inspection, it's not so reliable because we can measure something in the field, but when you're going to record this on a paper base or in a computer base, it can be some kind of problems making during this transition. So as everything in the world, we have advantage and disadvantage. But as I'm showing to you right now, we can say that there is more disadvantage than advantage in the manual inspection. And the context that we were made in this research, it also has some advantage and challenge. So we basically are in the off-site construction sector, specifically with precast concrete elements. So what are the advantages of the off-site construction in general? We have faster construction timeline, reduced waste and labor, better quality control, and greater modernization. On the other hand, we have some specific challenges. So we kind of way in the precast concrete elements, we have a dual standard compliance because we have the like a manufacturing environment and also the construction environments and with different standards. And we need to meet both. Huh? And also we have some kind of, depending of the precast elements and the density of the rebar, we have some cases of a very complex quality assessment. Huh? In a specific reinforcement cage, we can find very specific errors related to the quality, the dimensional quality of the final piece of the steel bar. And also, there is also some kind of defect costly fixes. So in every kind of aspect of construction, we have some advantage and also the challenges. And in this research, we focus on the specific challenge related to the precast concrete elements. And another thing which is very special and we need to highlight, and also it's part of the context, was a research opportunity. So back in 2022, CNPq, it's a funding agency in Brazil, they released a call for researchers, specifically to undergraduate students. And it was a 10-month scholarship. And at the time, they were developing at least two 10-month scholarships to in a way to promote artificial intelligence hackathons. So at the time, I had a conversation with Brenda, and we talked about this call from the CNPq. And at the time, it was right in the time that she was starting her capstone project, and everything went great. We applied, and we got the funding, and then we started this research. So the research gap that we were at the time trying to fill, it's like an iceberg because at the first moment we can say, okay, we have some technology limitations related to make the transition, the inspection to from manual to automated. But there is a lot of aspect that despite the technology limitation, we were aware. For instance, there is a high cost of to make everything in some way automated. Yeah? And there is also the cost of the softwares and the slow processing of the data when we're trying to digitalize this world. In a specific also barrier that we identified at the time, it's the accessible to small and medium enterprises. So at the time, we were trying to automate the task, but also make it affordable and to small and medium uh, enterprises. Because if at the time we developed a solution that was highly cost, it would be also a solution, but it would be restricted to a part of the enterprises. And we're trying to develop a solution that would bring also some advantage to small and medium companies in Brazil. So these were the barriers that at the time we were trying uh, to accomplish. And also, what we were trying to do at this research, we're trying to enhancing the reinforcement cage inspection. So we were trying to move from inefficient inspection workflow to a reliable and automated inspection workflow. And in order to move from an efficient to a reliable inspection process, we integrated three technologies. So we started with BIM integration, plus AI, plus mobile application. And why we were using mobile application? Because we were trying to keep some aspects of the manual inspection, which was the use of uh, basic tools. In a manual inspection, we use a tape, which is very basic. But even if we try to automate, we can still bring some aspects. And another thing besides tape, which is very basic in our environment, is the use of smartphones. So we can find everyone has smartphones, and maybe we can switch to automated inspection process, which is also uh, which is also brings some basic tools. Not so basic as a tape, as a measuring tape, but not as complicated like a laser scan. You know? So these were the three technology that we use at the time, and the artificial intelligence integration. Also, the rationale we were bringing them to the solution is the specific call from CNPq. So the FEV Smart integrates three technologies: BIM, computer vision, which is a specific uh, research field within the intelligent in artificial intelligence, and low-cost capture tools like smartphone cameras and lidar scanning. So these was the basic three areas that we try to bring together and try to develop how we're gonna integrate these three technology to move from a manual reinforcement inspection to automated reinforcement inspection. And the first one, the manual, which is very time consuming and also uh, prone to error by subjective measures, and how to transition this to fast and accurate and also accessible inspection process. It was not an easy task, but I think we figured it out a very promising approach to automate the inspection process. The research design that we developed, we followed a design science research approach, which is divided in these five stages: awareness of the problem, suggestion, development, evaluation, and conclusion. So we started with a research depth, through literature review, and also an empirical study at the precast company. And then we move on to the suggestion phase, which was the first time that we tried to develop even a um, preliminary aspect of the FEV smart system. And then we move it to the development stage, which was the stage that we selected a low complexity rebar assembly of the project because at the time, and still today, it's a prototype. So we cannot start a prototype with a very complex task. We need to start with a low complex, and then we select the specific elements, and we developed the bin model of these elements, and then we started to create a visual database for training the algorithm. So we took a lot of photos, specifically Brenda. She took a lot of photos to create this visual database. And after that, we moved to the evaluation stage to assess this prototype that we were developing. We used two criteria, transparency and efficiency, to measure how good or how bad was the prototype. And finally, at the conclusion stage, we finished and the final method to automated inspection. And also, we publish a lot of papers besides of this one here, and also ebook. I'm gonna talk a little bit more about this, the results, the outcomes of this conclusion later on. So basically, the outputs of each one of the research design. At the end, we would like to bring some recommendations for using this method. And now I'm gonna continue sharing with you some aspects of each one of the stages of this research. So starting with awareness of the problem. So as always, we started to find a very relevant research gap. So we went to the literature to the literature to find what was missing. And the first finding that we um, found at the time was the cost problem. So at the time, a very recent review paper on automated quality inspection brought us two main gaps: high cost and slow data processing. So basically, what was done until 2023 is researchers that tried to automate quality inspection of construction in general. They always end up in two gaps: high cost and slow data. Because most of the research at the time, they use a 3D laser scanner, which is a very good solution, but has a really high cost. It's and we were trying to develop for don't forget it. We were trying to develop solutions accessible for small and medium companies. So a Brazilian small or medium company would not have uh, enough money to even buy or rent a 3D laser scanner, which brings a lot of accuracy to the process. But it's something but as a solution so far from small and medium companies, no? And the other gap that this review paper show us is the slow data process. So we need to create a visual database, but it takes a lot of time to process this, to train the algorithm. And at least we around 50 to 50 minutes to 2.5 hours to process. So how come we're gonna automate something that it gonna takes more time? It doesn't make sense to us. So the manual inspection is very time consuming. How are we gonna develop a solution that takes more time than the manual one? So speed doesn't improve over manual methods. So these review paper really highlighted these two aspects of the literature review as a genre. So this was a perfect how can I say this? It was a perfect motivation for us because we were aiming exactly what the literature review point out as a research gap. And another aspect that the literature revealed to us that the data processing speed is slower than manual. Yeah. The reinforcement cage inspection, it was a major gap not addressed in past studies. Uh, Previous studies also focused on complex geometries, but they were always lab tested. They were not um, uh, investigated or in a real environment. No, the BIM and AI integration was another major gap and low cost solution. No previous stories focused on low cost solution. Most of them, and until today, they use laser scan, which is it is an amazing equipment, is an amazing, it brings a very good accuracy, but it's not a low cost solution for sure. Um, And besides the literature review gap, we also had at this stage company meetings and field observation. So Brenda was an intern in this company, in this precast concrete company from 2018 to 2022. And she had a direct engagement with reality. So the empirical aspect of the awareness stage was very present at the time because she was a member of the company. So and she attended a lot of company meetings and she was the intern. Um, she was a quality intern, which is an intern specific related to quality inspection. And and for those of you who are not from Bahia or Brazil, we had access to to this company and in fact, the research team had access to two companies. The a construction company of this group, of this Brazilian group, and also the precast company. So basically, it's a Brazilian business group of comprising four companies: a contractor, a real estate developer, a mining company, and a precast concrete manufacturer. And we had access to the precast factory and also to the contractor company. And this precast factory basically developing four structural products: pre-stressed structural elements, hollow core slabs, columns, and beams. And we focused at the time on one of the product, which was the beams. And we selected a project. It was a residential complex of 48 prefabricated homes. But as you can see here in these photos, they had a lot of columns and also beams in these detached houses. And then we selected low complex elements. So as you can see, the actual design was a 2D design. And then they didn't work at the time with uh, BIM models of the reinforcement cage. So we selected low density uh, elements, low density of steel bar, and we developed the BIM model of this BIM. And then we used three technology, as I mentioned previously. So the first one was a smartphone, Brenda's phone, which at the time she's no longer has this phone. She's upgraded because she's now an engineer. But at the time, as an intern, we used her phone, and it was a Samsung Galaxy SD Plus with this features here: camera resolution, processor, 8 giga RAM of memory, and the connectivity also aspect. So we used her phone, and then we also used an app called Polycom, which is an app that it's a paid solution, but she used at the time the free version, and that brings the LiDAR technology. With nowadays, we can find it also at the iPhone solutions as well. But basically, it's an app that capture image and generate 3D models. And finally, we use it a data processing technology. It's a cloud-based solution from Microsoft called Custom Vision that allows the users to train, test, and deploy custom image classification and object detection modules. Yeah. So basically, we have to follow three tasks. First, you upload the image to the cloud-based solution and the custom vision. And that's the reason why we had to, one of our challenge at the time was to create this visual database. So Brenda took a lot of photos in different angles, and this is also um, uh, a particular aspect of this method because depending of the lighting conditions and the angles of the photo, how you capture the reality, it made a huge influence at the final outcome. So we upload the image at the time on custom vision, and then we start to train. So you label some image to teach the custom vision the concept. Okay, this is a uh, this photo doesn't follow the quality standard. This one follows. So we need to start to train the algorithm, and at the end, the final task is evaluate. So it's basically API calls to quickly label image with this new computer vision model. So this was the AI solution behind the FV Smart. Uh, and what we have at the awareness stage as well. So Brenda attended critical analysis meeting during a 4 year period, and she reviewed some project minutes and documents. And at the time, one of the projects that were developed, they completed the project with 80 verification sheets completed and 0% of non-approvals. This wasn't an outcome of a critical analysis meeting. And I remember that Brenda told me at the time that the CEO of the company during this meeting said to her and everyone else that were there, how come can we get a verification sheet and 0% of non-approvals? There is some problem here. Because maybe the reason was exactly this. Adjustment were marked directly as approved. So they lost a non-conformity history. So in field, they made it some adjusted, but they didn't recorded this. So the fact that do not record it doesn't have a history of non-approvals brings a lot of problems to the company, especially when you have this amount of verification sheets. How come you can have 80 verification sheets completed and 0% of non-approval? This is not the reality of the company. So we spent she spent it all some 2 year. It was a 2 year effort, taking photos and getting direct involvement in this reality. And at the final stage of the awareness, the company and also us developed some proposed action. So uh, after all this analysis, the company uh, set up some actions. First one was to develop standard procedures were missing. They they had standard procedure, but not for all of the process. Conduct on-site training and monitoring. Improve the mobile tool for verification sheets. Hold weekly or bi-weekly data analysis meeting, and also update training or on standard procedure. So at the time, the company was very aware of these problems and very, I would say, concerned, and but also focused on trying to improve this and make the quality inspection better. And this was the awareness stage. It took us a lot of time to review the literature and also to get in touch with the reality. But after this, we move on to the suggestion phase. Then that was the phase that we started to develop the FEV Smart. So the objective at the time was support workers in this check verification to improve quality, speed, productivity, and data reliability. Uh, and one thing that is was very interesting that we took insights not from this company. Brenda developed a questionnaire and applied to her fellows at the to her fellow colleagues that were also interns in different construction companies in Bahia, and to try to we're trying to define the ideal activity. Which one would be better um, to select, to study, and to develop the FEV Smart? So we have some basic following criteria. So it would be a task with high relevance and impact on process quality, urgently highlighted by stakeholders, which was the production staff and also the interns. Few variables would say it can be something that is not very complex. A common activity across multiple projects and a high potential also for being modeling. So the preliminary method, the FEV Smart, was an 8-step method. So the first one was mapping of the standard assembly procedure. And the second one was mapping of verification sheet items. And the third one, we needed to, okay, we cannot automate all the items of the verification sheet. Which one of them is we can automate, and which one of them we cannot automate. And then we move on to the selection of the task to be verified, develop the bin model of the reinforcement cage, capture the reality, capture the reinforcement cage already assembled, and to create this visual data set for training the computer vision model, and finally use the FEV Smart solution. So I forgot to mention one thing that we use it. We did not develop the AI model. We use it a solution that is commercial, available, the custom vision. And these were I'm gonna talk this about further details, but use the reason why you used a computer vision model, in fact, is because we did at the time we didn't have much knowledge on AI. And even Brenda, myself, including also Alison. So we used this model also because as a first step intention to integrate AI. And then after the suggestion phase, we move it to the development stage. So I brought you here some key findings of this stage. So the FEV Smart app uh, can automate the verification sheet. We can some items, not all of them. So one of them is bar length. We can detect the length of the bar. The other item of the verification, even the item that, sorry, the other item of the verification sheet that we can automate is the number of bars and stirrups. And also doing this, we can compare between the BIM model and the reality. Spacing is also an item, which is checked. But in reality, workers, they mark the spacing with chalk. So as you can see in these images, if the spacing is correct, the marks are not visible here in this photo. And if it is incorrect, as you can see here, the guide mark remains visible. Rebar tying also as well is a item on the verification sheet that we can use in the FV Smart. But it's something that in fact, we don't need an AI algorithm to check this because it can see visible in the image if the bars are tied or not. And then these were the items that we selected to be in the FEV Smart. And and then we move it to the evolution stage. So the objective here was to analyze the performance of this prototype and, and verify if the accuracy of this automated inspection of reinforcement cage assembly. So the procedure here was test the prototype using real image captures on site, compare the results of the computer vision model with manual verification, and we used three parameters: precision, recall, and average precision. And then at the time we use it, as I mentioned to you, Brenda took a lot of photos, and at the time we were trying to see which one had the best lighting condition. So as you can see here, these first two, uh, these are some examples of image that at the field with a construction background. You can see other store areas. You can see the trees. You can see the sky. You can see the land. We can see the other types uh, of reinforcement cage stored over there, and we came out with this kind of environment here, which is the single uh, beam that we developed, that we selected with a wide background. So this is also in an area in the factory, but not outside. In this condition here with a wide background, we had better results with this one here. As you can see, when you use the polycam, some part, even with this wide background, we don't have so many accuracy in the the length of the bar. As you can see here, we can see some part of the length. These are very preliminary results that we were still trying to figure out which was the best condition to capture reality. Even though we don't have the very, I would say, accurate, accurate image of the beam, with the polycam, we can still measure the bar length. So this was completed at the time, even without some accuracy in the reality here. It is still possible to measure the balance. And these were the three criteria results. So we reached a precision of 72.6%, a recall of 68%, and an average precision of 81.1%. Uh, so just to give you a reference, a precision above 80% and a recall above 70% are generally acceptable as a reference value. We didn't have a precision. We do. Sorry, we did have a precision above 80% and recall around 70. So it was not that bad. And to calculate this metric is we also consider some aspects. So first, we had to follow these criteria here: true positives, true negatives, false positive, and false negative. So which is true positives are elements that are correctly identified with the app. True negative elements correctly predicted as absent. False negative elements incorrectly predicted that did not exist. And false negatives existent elements that were not identified. So we had to calculate these metrics using this true and false, positive and negative aspect, and came out with a confusion matrix to analyze all the performance of the prototype. So now we're moving to the final stage of the research, the conclusion stage. So the objective was to consolidate the results and formalize the FV smart methods. And what we carried out at the time, we made a critical review of the test and the model performance. We identified the limitation and improvement opportunities. We made some recommendations to use the method in real construction sites. We formalized the procedure, structure clear and replicable phases, and also we made a lot of communication of this research to the scientific community and also as to the society as a whole, as you can see, as you're gonna see later on. So this is the final uh, SV Smart method, the current one. We did not yet improve it so far. So basically, is a method of three phases. The first phase is image acquisition. The second one's image processing and analysis, and the third one is the when you issue like a verification sheet, a digital version of a verification sheet. So the first phase, the image. Sorry. Uh, Before starting this first phase, we have some requirements. So we need to have the pin model of the element that we need to inspect, at least in a level of development of 300. And also we need the ICC version of this model. And we need we need to have the element that are already assembled, completed to take photos. So these are basically the three inputs to the process. So and then we start with the first one, the image acquisition, and then the objective is capture the reality. Yeah? And here you can find the object of each one of the phases, the people that we need in each one of these phases, and also the tools. So basically here is the people that we need at the reality capture phase is someone that is responsible for the reinforcement cage inspection. Yeah? This person will take photos. This person will capture the reality with the smartphone and also using the polycam app. So basically, you need a smartphone with camera for scanning, and And then you follow a person, follow two steps. Step one, ensure prior verification of the smallest dimension of the reinforcement cage assembly to determine the most suitable method of capturing. So you need to figure it out the better conditions for to take a photo, to scan it, or even a combination of those. What would be the better space, the better lighting condition, the better surrounds to take a photo and scan with the app. So these depend of the elements. At the time we had a, a building, but this if it was a column or a hollow core slab would be different. Then, and then after you identify this condition, you move on to the second step, which is ensure prior verification of the image capture environment, considering such as lighting condition and the presence of other objects within the camera's field of view, right? And then capture the image. After this, we move on to the second process, which is data process. So first you collect data, and now you process your data. And it can be the same person as well, like capture the reality. But now that we came on to the part where we need to train the algorithm to identify the errors in the reinforcement cage assembly. So basically, you need a computer with internet access and AI solution. We use the custom vision, but it could be another one. Or if you have AI skills, you can develop a specific algorithm for this. And you need a license of a BIM software. uh, And then you follow three steps. First, transfer the capture image to the computer or the cloud-based solution. Then separate the image that do not require BIM modeling for comparison from those that do. Upload the relevant image to the AI solution and upload the relevant image to the algorithm that integrates BIM and image capture for comparison. And these two phases uh, we followed each one of these aspects uh, in the field. But the third one is still an idea. We did not develop this because this is the final solution. You know, a more it's not a prototype, but now the third phase represents a commercial product. That would be the FV Smart. Né? So basically, here the object of this third phase is to bring the checklist, a digital checklist, and as you can pick as approve it, not approve it, or does not apply. Basically, the same person, and now with a smartphone or a computer with the FEV Smart, uh, which is not developed yet. It's not, unfortunately, it's not available yet. It's still in the development stage. So basically, but if it was, the basic uh, steps that we would follow in this FEV Smart app would be load quality inspection checklist results, document the observation for unapproved items, including issues that you identified in the field or corrective action that it is necessary. And the final step would be generate the final inspection reports in PDF file or even in the in the in the in the screen of a smartphone. So the outcome of this method would be like a information to support managers in decision making, né? With reliable data and cost accessible and uh, with in a not in a real time, but taking less time than a manual inspection process. So to sum up, Brenda, uh, she got an award by the Salvador city. Uh, she took the first place in the 2023 entrepreneurial undergraduate thesis program. Uh, I don't remember, but she received a money award. I don't remember. It was not enough for her efforts, but it was a recognition of her hard work on this. And I think the award also included a course where you can understand and better the how to to make this research a real business. So this was also her intention. She's really keen to research, but she all at from the beginning, she always wanted to bring a commercial solution, something that as everything is starting as a in a research stage, and then we move on to a commercial solution where we can um, sell to small and medium enterprises company. And this was also research that besides the papers, I think we reached the society as a whole because she was also invited to a podcast and which she presented her undergraduate research in Portuguese to I think would say a broader audience than the academic environment that we were already used to. We acknowledge this research to this NPQ and also the company that provide data for this study. And the future vision here, what I would like to finish is the research is not finished. As I told you, this was uh, undergraduate research. And then I think she was very motivated with the awards, the outcomes that she reached with this research. And then she decided to continue pursue this in the master level. She's now a master student, as I mentioned earlier. And now in her master's studies, she's trying to further develop the FV's market. So she's learning more about AI solutions and the future vision to the FV's market is try to scale up this prototype beyond reinforcement cages to other more complex uh, rebar elements, advancing AI algorithms for real-time or on-site inspections, trying in some way democratize in, in another way to bring the solution to a whole spectrum of companies, not just huge companies or big companies, but also to small and medium as well, and also the precast concrete industry, and build safer and more efficient construction globally. So this research, as I mentioned right in the beginning, it's a very it reaches places that I never imagined. So it started in Portuguese. Last month, I presented this research here in Chile in Spanish, and now I'm presenting to you and to the world because this is going to be on the YouTube in English. So it's an undergraduate research that reached so far. So I truly believe that this research has a huge potential, I think, and also to bring not besides the impact and the awards and the and the audience that reach it, but also I forgot to mention that now in her master's studies, we're trying to integrate a different technology. So we end up here with them, smartphone and AI. And in her master's study, we're trying to bring another technology, which is the uh, augmented reality. Augmented reality or virtual reality. We don't know yet. That would be a technology that would bring a lot of advantages and improvements to the FEV market. And that's it. Thank you very much for your attention.